Hello, Geometry. This is Mrs. Peterson. We are doing lesson 2.2, inductive and deductive reasoning. The essential question for today's lesson is how can you use reasoning to solve problems? So we're first going to start out with this pattern, and I want to know if you guys, I want to see if you guys can figure out, identify any patterns in this image to the right. This is really fun to do in class, and I'm sad that we don't get to do this, but if you could pause it and see if you can figure out that pattern, that would be super cool. I think I only had one student figure it out last year. Okay, hopefully you were able to look at this pattern and maybe you came up, there really are technically two different ways that I've seen students come up with this, but how you would do this is you have 1 plus 1 and that is 2. So, and then you've got 1 plus 2 gives us 3. 2 plus 1 gives us 3. And notice that 1s are all along the outside. So 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And we've got 1 plus 4 is 5. 4 plus 6 is 10. So on and so on. So please let me know if you guys end up getting this in class. Come and tell me. I think it would be really cool to see that. And maybe you came up with a different pattern and I would love to see what you did with that. Okay, let's move on to the lesson. So it says a blank is an unproven statement that is based on observations. Okay, so a conjecture. A conjecture is kind of like, I want you to think about science, it's kind of like a conclusion. You go through all of this lab and what conclusion can you make? What conjecture can you make? Is an unproven statement that is based on observations. You use inductive reasoning. When you find a pattern, so highlight this in specific cases and then write a conjecture for the general case. So inductive reasoning is when you use patterns and sometimes you use observations. Actually, it's right up above here. So we're going to learn another reasoning, and that one is not based off of patterns or observations. It's based off of logic and facts and definitions. But inductive reasoning is, what do you notice? What do you observe? What pattern do you see? And what kind of conclusion can you then make next? So example 1, describe how to sketch the fourth figure in the pattern, then sketch the fourth figure. So let's look at this. I want you to come up with this next fourth figure. So if you want to pause it and try it on your own, I always like to see what kids come up with before me showing you. So pause it, but I will show you the fourth figure here. So if you noticed, obviously we've got a circle, okay? And this first circle is being cut into 2 equal parts. Now, that line was then cut into 2 more equal parts, so making that 4. So we had this original one. So original. Now we are then cutting into 2 more equal parts. So you are technically cutting it into equal parts. So this one just had 1 line cutting it into equal parts. This had 2 lines cutting it into 4 equal parts. This one had 3 lines cutting it into 6 equal parts. And now this one's going to have 4 lines cutting it into 8 equal parts. Now, there's something about this shading that's going on. Okay, this shading is located above the horizontal line and to the left. So if we were to shade, should be this one right here based on that horizontal line. So that is figure 4. It says describe how to sketch. You can go ahead in your own words, say that you are adding 1 more line and cutting it into equal parts. And the figure left and above the horizontal line is shaded in. Okay, go ahead and try this one on your own. Sketch the next figure in each pattern. Okay, And these are my figures you can probably draw way better than I can. Okay. Example 2, numbers such as 3, 4, and 5 are called consecutive, like 1, 2, 3, 7, 8, 9. These are called consecutive integers. Make and test a conjecture about the sum of any 3 consecutive integers. So this is kind of like our experiment here, okay? So we're going to test some values and we're going to figure out what is the result when we test them. So let's just pick out some keywords here. It says, make and test a conjecture about the sum of any 3 consecutive integers. Sum means to add, and any 3 consecutive integers. When they say integers, that could be positive or negative. Let's keep it simple and have them be positive. But the sum of 3 integers, so let's do 1 plus 2 plus 3. That's consecutive. Okay, and that gives us a total. When you add them up, you get 6. Okay, let's try another one. 4 plus 5 plus 6. You get 15 when you add those together. 7 plus 8 plus 9. You don't have to be picking these ones. You can be trying your own. 10, 11, 12. Okay, so I like to do this in class because I always like to see if students are getting it by the second test. Now, sometimes you only need 1 test and you can figure it out, 1 or 2 tests. And a lot of kids have a difficult time figuring out what's happening from the first test to the second test here. So then I do a 3rd one and I see if you notice. And then I do a 4th one and I see if you notice. And a lot of kids will guess at this, but really what's happening here is, I want you to look at this middle number and how I get a 6. This middle number and how I get a 15. This middle number and how I get a 24. And how I get a 33. So if you look at that, 2 times 3 is 6. 5 times 3 is 15. 8 times 3 is 24. 11 times 3 is 33. So it says we just tested, we got the result, we are now seeing the pattern, we're observing what happened. And it says now make a conjecture. So here's my conjecture. I always start with how they wrote it, okay? The sum, I'm just copying this down, of any 3 consecutive integers is, okay, now what did we say? Well, that middle number is the middle integer multiplied by 3. So if you were to take 119 plus 120 plus 121, you could easily figure that out without adding those 3 integers together based off of this conclusion that we just made. Okay, go ahead and make some tests, test your conjecture, and come up with your conjecture. So the signs of the product of any 3 negative integers. What happens when you product? That means multiply any 3 negative integers. So pick 3 numbers that are negative, multiply them, and see what happens. The sum of any 5 consecutive integers. I'm going to tell you, it's going to look really similar to this. Okay, so go ahead and try that out. Press pause. Okay. Okay, so when you take 3 negative numbers and multiply them, you maybe already know this rule. Some of them are obvious, okay? 3 negative numbers multiplied gives you a negative every single time. And then when you added 5 consecutive integers together, you took 5 times the middle number. Okay, to show a conjecture is true, you must show that it is true of all cases. You can show that a conjecture is false, however, by finding just one counterexample. Okay, one counterexample. A counterexample is a specific case which the conjecture is false. So a conjecture is true as long as all cases work. But as soon as you find just that one that makes it false, then it would make the entire conjecture false. So I always like to say, you're going to hear me tell stories in this lesson today to kind of help you remember. So I always say, okay, maybe you always want to prove your parents wrong, or maybe I always say, there's that person that always wants to be right, and you're just trying to find that one example that proves them wrong. That is what a counterexample is. You just need one to prove them wrong. So it says a student makes the following conjecture about the sum of two numbers. Find a counterexample to disprove this student's conjecture. So once again, maybe your parents say this, or maybe that person that's always right says, well, the sum of two numbers is always more, is always more than the greater number. Okay. So you need to think about, how can I prove this person wrong? The sum, okay, we're adding, of two numbers, they don't specify whether they're positive or negative, is always more than the greater number. Okay. So for me, I'm thinking about, let's think about numbers. If I do the sum of 2 plus 3, this is always, in this case, greater than the larger number. 5 is greater than 3. That did not prove that person wrong. They're still right. Okay, so then you pick another one. So you pick, maybe you pick 10 plus 3. Well, that's 13. 13 is bigger than the greater number here. 13 is bigger than 10. So that also didn't work. So let's think about something else. What about 0 plus 1? Okay. Is 1 greater than 1? Think about that. Is 1 greater than 1? So this actually works because 1 is not greater than 1. It's equal to 1. So it says the sum of two numbers is always more than the greater number. So looking at this, 0 and 1 are our counterexamples. Okay, so go ahead and try this on your own. You're finding a way to prove this wrong, and you just need one. So zeros and ones will work really well with a lot of these statements. Also try negative numbers. Okay, here are the answers. The value of x squared is always greater than the value of x. So if you tried 2, 3, 4, that would have proved it true. But we want to prove this person, whoever's saying this, wrong. Well, if you take x equals 1, if you take 1 squared, that's not greater than 1. So that's the counterexample. And down here it says the sum of two numbers is always greater than their difference. Difference means to subtract them, okay? So the sum of two numbers, well, they don't specify if they should be positive or negative. So as long as one of them is negative, it proves that statement wrong. Deductive reasoning uses facts, definitions, accepted properties, and the laws of logic, which are right down below, to form a logical argument. So the laws of logic are the laws of detachment and the laws of syllogism, okay? Next to detachment, I want you to put detention. I'm going to tell you a little story about how to remember the law of detachment. So the definition of this, you can go ahead and put it on pause for what you need to fill in. But it says, if the hypothesis of a true conditional statement is true, then the conclusion is also true. So let's think about this. We have a rule at our school that says, if you are tardy 3 times, then you get detention. Okay, so if you are tardy 3 times, then you get detention. That is a true conditional statement. Okay, now let's make a hypothesis of some sort. Let's say that Nick is tardy 3 times. Based off of that rule of if you're tardy 3 times, then you get detention. If Nick is tardy 3 times, what can we say is going to happen to Nick? hopefully you can come up with he's going to get detention based off of that rule. So think about that detention problem, about using that law of detachment, because some kids tend to overthink that. Okay, I'm going to come back to law of syllogism in just a second. So let's think about that detention problem. If two segments have the same length, then they are congruent. Okay, so that is, kind of think about this part as your rule. Okay, so if two segments have the same length, then they are congruent. Well, now we're giving some example of that. You know that BC is equal to XY. So these are two segments that have the same length. What can we say about these two segments? It says use the law of detachment. What statement can you make? So if two segments have the same length, which BC and XY do, then they are congruent. So what can you make? Well, if BC is equal to XY, based off of that rule, BC is congruent to XY. Just like the rule of being tardy 3 times, you're going to get detention. Okay? Okay, so keep that in mind. You can come back and answer this, write something to each law of logic to help you remember what to do. Okay, if you want to, you could put law of detachment, detention problem. Okay, now go ahead and try number 7 on your own. Okay, if 90 degrees is, or sorry, if the measure of angle R is greater than 90 degrees but less than 180, then the measure of angle R is obtuse. That's that rule. Okay, if you're tardy 3 times, then you get detention. That's the rule. Okay, the measure of angle R is 155 degrees. What can you conclude about that? It's between 90 and 180, so you can conclude that the measure of angle R is obtuse. Okay, I'm going to go back to the law of syllogism. So if you wrote this down already, I want you to add this in there. If the hypothesis P, then conclusion Q. If hypothesis Q, then conclusion R. Then you can conclude, this is going to be your final answer, if the hypothesis P, then the conclusion is R. So this is how I do this. I like to use symbols, okay? They give you a statement, if P, then Q, and they start the next sentence with that Q statement, if Q, then R, you can then make a link. If P, so whatever's first, if P, then R, you've got your hypothesis and your conclusion. Okay, this is going to be your final statement. You might also see it like this. If P, then Q. If R, then P. And your conclusion would be, this link is happening right here. So you want to say whatever your hypothesis is, if R, then Q. Okay, now let's apply that to a statement here. And that's just what I wrote on the left-hand side. Okay, so example 5, we're using the law of syllogism to write a new conditional statement that follows from the pair of true statements. Okay, so it says, if x squared is greater than 25, we're going to call that P. Then x squared is greater than 20. We're going to call that Q. If x is greater than 5, that wasn't P, that wasn't Q, so this must be R. Then x squared is greater than 25. Where have you seen that before? Well, x squared greater than 25, x squared greater than 25, that's P. So let's write this off to the side to make sure this is even a true statement. They said if P, then Q in the first sentence. There's the first sentence. The second sentence says if R, then P. Is there something that was a hypothesis and then came a conclusion, or something that was a conclusion and then became a hypothesis? Was there a link? There absolutely was a link made here. So we can then say if R, then Q, but we need to use that from our statements. So I'm going to go ahead and write this out. Let's find R. R is right here. If x is greater than 5, then, well, we need to use Q. So x squared, then x squared is greater than 20. So this was a true law of syllogism, and based off of this link that happened, we were able to link the hypothesis of R to the conclusion of Q. Okay, let's check this next one out. If a polygon is regular, that's P, then all angles in the interior of the polygon are congruent. Call that Q. If a polygon is regular, I have seen that before, that's P. Then all its sides are congruent. I have not seen that yet, so we're going to call that R. Let's make sure that this can even work. So the first sentence is if P, then Q. Looks good so far. But then the next one is if P, then R. There is no link. This cannot link to each other because it was the hypothesis of both statements. So here you would just say not valid. No link was made. Whoopsies. Okay, go ahead to the left side and try those ones on your own. Okay, so this one did make a link and it linked P to R. So hopefully you got, if you get an A on your math test, then you can watch your favorite actor. Okay, example 7. If example 6 is in your notes, will you cross it out? We're not going to do that. And if you go to the left side, number 9, we are not going to do that problem either. So we're going to go straight to example 7. It says decide whether inductive, okay, remember these are patterns and objectives. Observations, not objectives. Observations. And then you've got deductive reasoning. These are laws, definitions, facts. Is used to reach the conclusion. So decide whether inductive and deductive reasonings are used to reach the conclusion. Explain your reasoning. So each time Monica kicks a ball up in the air, it returns to the ground. So the next time Monica kicks a ball up in the air, it will return to the ground. So there are some kids here that say, well, that's deductive because that's the law of gravity, that when something goes up in the air, it comes back down. But the way that they're wording this is not saying, oh, based off of the law of gravity, if a ball goes up in the air, it comes down. The way that they stated this is each time Monica kicks a ball up in the air, it returns to the ground. They're observing Monica kicking a ball and it coming back down. So because they're observing this is inductive. This was an observation. Okay, all reptiles are cold-blooded. Parrots are not cold-blooded. Sue's pet parrot is not a reptile. Okay, we're not going to test if a reptile is cold-blooded or that a parrot is not cold-blooded. This is all based off of facts. So this is deductive. These are all based off of facts and logic. Okay, go ahead and try that on your own. Decide whether this is inductive or deductive. Okay, it is deductive. They're using facts, but this was also a law of detachment. All multiples of 8 are divisible by 4. 64 is a multiple of 8, therefore it is divisible by 4. That is a law of detachment, which once again is deductive. So go to the bottom and fill out the summary. 3 things I learned, 2 things I found interesting and helpful, 1 question that I still have. And then we're going to move on to 2-3. So go ahead and pause, fill this out, and then we're going to move on to 2-3. Okay, when you're ready, go ahead and write down this essential question, lesson 2.3, postulates and diagrams. The essential question is, in a diagram, what can be assumed and what needs to be labeled? So this first activity that we're going to do is proving to you that we don't want to make assumptions. Okay, so go to the left-hand side and try this. In the first image, do you believe that the horizontal segments are congruent or not? Why? In the second image, do you believe that the horizontal segments are parallel? Why or why not? So go ahead and pause this and look at that. And come up with what do you think is going on here? Do you think that those horizontal lines are congruent in that first figure? And do you think the horizontal lines are parallel in the second? Yes or no, and why do you think? Okay, so hopefully you were able to look at that. It does look very skewed because of these little arrow things at the end of these horizontal lines, but these horizontal lines are actually congruent to each other. You can make them look like they're not congruent based off of those end arrows that can skew your view. So don't assume that they're not congruent based off of what they have on there. And then this next one I just think is super cool. It looks like those lines are like slanted in that they'll intersect, but they actually aren't. So if you were to draw these horizontal lines, if you were to look at them without trying to imagine those black blocks there, these actually are completely parallel lines. Those black boxes skew your vision. Okay, so kind of a cool thing to look at. So don't ever assume things in geometry. Okay. So if you don't have this in your notes, you're going to want to write this out. So 2-point postulate. I will not make you memorize that 2-point postulate is 2.1. Okay. Line point postulate, I'm not going to make you memorize that that's 2.2. But 2-point postulate, I do need you to know that the 2-point postulate states through any 2 points, there's exactly one line. Line point postulate states a line contains at least 2 points. 2.3, you don't need to memorize that, but line intersection postulate, we've talked about this already. If 2 lines intersect, then their intersection is exactly 1 point. And you should be drawing these pictures off to the side as well. 3-point postulate, through any 3 non-collinear points, there exists exactly 1 plane. Plane-point postulate, a plane contains at least 3 non-collinear points. Plane-line postulate, if 2 points lie on a plane, then the line containing them lies in the plane as well. And plane intersection postulate, if 2 planes intersect, then their intersection is a line. So go ahead and pause wherever you need to make sure you're writing those down and drawing the picture. Okay, let's go to this first one. State the postulate illustrated by the diagram. Well, what I see here is that if 2 lines intersect, then they create a point. So when you're looking at that, to me, that's line intersection postulate. If 2 lines intersect, then they intersect at 1 point. So I'm going to call this, you don't need the 2.3. What I'm more interested in is you saying line intersection postulate. Okay, for B, I'm noticing 2 planes intersecting and that their intersection creates a line. So refer back to those postulates. And for me, once again, you don't have to do the 2.7, but I like to see that you're saying that this is plane intersection postulate. Okay, go ahead and try this next one on your own. Use the diagram in example 2. Have it up on the board. Which postulate allows you to say that the intersection of plane P and plane Q is a line? So 2.7, plane intersection postulate. When 2 planes intersect, they create a line. Use a diagram to write an example of plane-point postulate and plane-line postulate. So plane-point postulate. So plane-point postulate states this. A plane contains at least 3 points. So for me, I want to find a plane that contains at least 3 points. I see B, A, and C all on plane P. So I'm going to state plane P contains points A, B, and C. So that's for plane point. For plane line, okay, for plane line, that one states, I gotta find this here, plane line, if two points lie in a plane, then the line containing those points lie in the same plane. So this is how I'm going to say this one. So I'm going to find 2 points and a line. So I see B and A. What I'm going to say is B and A lie in plane P, therefore the line BA, or line N, is also in plane P. So B, whoops, and A both lie in plane P. Therefore, the line containing them, so BA, is also in plane P. Okay, go ahead and try this next one on your own on the left-hand side. You're using that same picture. Okay. Here are the answers to those. Okay, example 3, sketch a diagram showing line TV intersecting segment PQ at point W. Ooh, be careful with this. So TW is congruent to VW. So TV is a line. TV. Notice this is a line. I'm continuing on in both directions. And it is intersected by PQ, which is a segment. But what's really, you have to be really careful with this, is that TW and VW, so basically W is in the middle. So let's put W in the middle. These need to be congruent. And PQ, we don't really care about where that falls. PQ, we care that it falls in the middle of TV, but we don't, it doesn't say anything about PW or QW being congruent. But it's, let's look at this and read it again. Now that we have the picture, let's look at that. Sketch a diagram showing TV, okay, we got line TV, intersecting PQ at point W. Well, when two lines intersect, they make a point. That's where W comes into play. So that TW is congruent to VW. Now notice, to show my congruence, I had to put those dash marks in. Okay, so this diagram is done. Now, in the diagram that you just made, it says if the given information states that PW and QW are congruent, how would you show that in the picture? How did we show that the other ones were congruent? That TW and VW was? And then go ahead and answer number 6. Okay, you got to use dash marks. And then it says, name a pair of supplementary angles in the diagram. You could have used basically all of these, okay? You could have used these two, okay? You could have used these two, or these two, okay? So there's many answers for this. I just chose 2 of them. Oops. So I said TWP and PWV. And yes, they are a linear pair. Okay, a line is a line perpendicular to a plane if and only if the line intersecting the plane in a point and is perpendicular to every line in the plane that intersects it at that point. So one thing that I just want to really bring up in this picture is this. A lot of kids will say, well, it looks like it's a right angle. Never, ever, ever assume that it's a right angle or perpendicular unless it has those boxes. Okay. So we want to say whether this is true or not, whether we can assume it or not. So I'm going to say true, you can assume it, or false, no, you can't assume it. So it says, which of the following statements cannot be assumed for the diagram? So looking at this diagram, it says points A, B, and F are collinear. Well, let's look. A, B, F, are they collinear, meaning on the same line? Yes, that's true. You can assume that because they are all on the same line. Okay, points E, B, D are collinear. So E, B, D are collinear. Well, they could possibly be collinear, but we can't assume that because a line isn't going through it. When you have 3 points, the line actually has to go through it in order to assume that. So you would say false for this one. AB is perpendicular to plane S. Well, I better see that little box in order to show something's perpendicular. AB is perpendicular to S. It has that box there. So yes, that is a true statement. CD is perpendicular to plane T. Oops. Well, plane T, cut it off again. Plane T is this one right here. And it says CD is perpendicular to that. I do not see a box there, so you cannot assume that. And then AF intersects BC at B. So let's look. AF intersects BC at B. That is a true statement. Okay, go ahead and try these last ones on your own. Okay, here are the answers to those. Okay, summary, make sure that you answer that essential question and you can answer it right in that summary area. Good luck.